All right. Hello. Welcome back, everybody. We are continuing through Chapter 6, where we are talking about z-scores and the normal model and how we can use those things to compare. Okay. So in our last video, we talked about shifting and rescaling data and how a z-score is essentially a shifted and rescaled set of data. And it created a model where a distribution that was centered at 0 and had a standard deviation of 1. Okay, so in this video, we're going to talk a little bit about how we know what a z-score, like how do we know when a z-score is big, right? What is a z-score telling us? And we're going to introduce this thing called the normal model. All right. So let's go ahead and move forward here. So a z-score gives us an indication of how unusual a value is because it tells us how far it is from the mean, right? Rescaling something tells us that it's this many standard deviations away from the mean. If it's sitting at 0, a z-score of 0, it means it's right at the mean. It is directly in the center. It's at the mode of this distribution. A z-score of 1 tells us that it is 1 standard deviation above the mean, and a z-score of -1 means it's 1 standard deviation below the mean. So it's this much, it's that distance away. Remember, standard deviations when we're talking about a z-score is a unit of measurement, okay? So how far from 0 does a z-score have to be considered interesting or unusual? Well, there isn't a universal standard. However, the larger a z-score is, whether it's negative or positive, the more unusual it is, right? Remember, the average at the center is where it happens most often. If it's larger, anything farther away from 0 is more and more unusual. And again, negative z-scores tell us that it's below the mean. Positive z-scores tell us that it's above the mean, okay? So while there's no universal standard, there is a model that shows up over and over again in statistics, and it is called a normal model. Or you may have heard of it as a bell-shaped curve. It's these curves that I've been drawing these last couple of videos. This is a bell-shaped curve. It's called that because it's shaped like a bell, right? It's also called the normal model. We only use these models when our distributions are unimodal and roughly symmetric. So if you have a, we're talking in this case, if your histogram looks kind of like this, right? Relatively unimodal and symmetric, we can use the normal model to approximate things. These distributions provide a measure of how extreme a z-score is. So before we talk about the extremity, let's just talk a little bit more about the normal model. Okay, there is a normal model for every possible combination of mean and standard deviation. The way that we notate this is through n of mu comma sigma. Okay, so this represents the normal model where the mu is the mean and the standard deviation is the sigma. Okay, we're using Greek letters to define this because these are not numerical summaries of data. They are part of a model. They don't come from data. We're not getting the mean and standard deviation from looking at a set of data. They're numbers that we are choosing to help specify the model. We call these parameters of the model. So just to say here, if we have n of 25, 5, that is a normal model with a mean of 25 and a standard deviation of 5. Okay, that's all that notation means. It means we have a normal model. It is roughly unimodal and symmetric. The center is at 25. The standard deviation is 5. So every time I go a standard deviation out, I'm moving out 5 data. All right. Now, Summaries of data, like sample mean and standard deviation, are written with Latin letters. We call these things statistics. When we standardized the normal data, we still call the standardized value a z-score, and we write it like this. So again, notice here we're using parameters. Okay, we're using model values to calculate the z-score here. Again, it's kind of just a way of defining it. In a lot of ways, the sample mean and the model mean are very similar. So it's not like we're saying things that are significantly different here. But just so we're clear, the difference between parameters and statistics. So as a summary, okay, a parameter comes from a model. And we're using the mu symbol when we do that for the mean, and the sigma symbol when it's for the standard deviation. Okay. Again, this is when we're defining a mathematical model. That is different than when we are calculating a statistic. Statistics come from real life data, right? They come from us taking a survey and finding like 50 different numbers and then calculating the mean of that. Okay. That's a funny looking eye. Sorry, this is real life. This is real life data. Okay, statistics come from real life data, and when we calculate it that way, it's the bar over the top is what signifies the mean, and the standard deviation is usually just S. Sometimes we do it S sub X to show that this is the standard deviation of X, and this is the standard deviation of Y. Okay, so parameters come from models. Statistics come from real life data. They are very similar in nature, but we do define them differently because sometimes we're looking at the model and sometimes we're looking at a real life statistic. Okay, so once we've standardized these things, we need only one model. Once we've done taken z-scores for everything, we need one model. It's called the standard normal model, and it is a normal model with a mean of 0 and a standard deviation of 1. Okay, we did this at the end of the last video. Once we have standardized all of our data, meaning we've taken every single data piece and we have calculated a z-score, we've created a model that has a mean of 0 and a standard deviation of 1. But be careful. We don't use the normal model for just any data set, right? Standardizing does not change the shape of a distribution. So before we use the normal model, we have to make an assumption that the distribution is normal. In practice, we can't typically check that, so we check this following condition. It's called the nearly normal condition. And basically, it's before we do anything, we make sure that the shape of the data's distribution is roughly unimodal and symmetric. We can check it with a histogram, or we can create a normal probability plot. However, we have to make sure, before we do anything else that we're going to talk about for the rest of this chapter, that the distribution we're talking about is nearly normal. So again, roughly unimodal and symmetric. Okay. Once we've done that, we can start talking about things like the 68, 95, 99.7 rule. So normal models give us an idea of how extreme a value is by telling us how likely it is to find one that far from the mean. This is why the models are kind of important. They tell us exactly how rare something is based on the z-score of a particular piece of data within a distribution. We can find these numbers precisely, and we're going to do that in the next video. But until then, we're going to talk about this rule that tells us a lot about the way a normal model works. And it turns out that in a normal model, about 68% of the values fall within one standard deviation of the mean. About 95% of values fall within 2 standard deviations of the mean. And about 99.7, that is almost everything, falls within 3 standard deviations of the mean. So here's a picture of that rule. So here's our normal model, and at the center here, that's 0. This is my mean, right? My mu, okay? Then if we go over 1 standard deviation, both negative and positive, 68% of the data. So if I had 100 pieces of data, I surveyed 100 people, and the top 5 answers are up on the board. No, the top 5 answers are here. 68 of those 100 people are going to fall within 1 standard deviation of the mean. 2 standard deviations of the mean is going to be 95% of the people. So if I had 100 people surveyed, 95 of those people are going to fall within 2 standard deviations of the mean. And finally, 3 standard deviations away from the mean is 99.7%. So of the 100 people that I surveyed, 99 of them, 99.7 of them are there. Or if I surveyed 1,000 people, 997 of them would be between 3 standard deviations of the mean. Okay? So this model, normal model, and using this 68, 95, 99.7 rule gives us an idea of just how rare something is based on the z-score. Because you can see that anything above 3 is really rare. Anything within 2 or 3 is pretty rare. Things within 0 and 1 are fairly common. Things between 1 and 2 are somewhat uncommon, okay? So it all depends on what the z-score is.
Also, a girls' basketball reminder, there is open gym on Monday and Wednesdays from 6 to 7:30. Thank you.
So let's do a problem here where we actually do some calculations using the 68, 95, 99.7 rule. So, as a group, the Dutch are among the tallest people in the world. The average Dutch male, or Dutch man, is 184 centimeters tall. That's just over 6 feet. The average Dutch woman is 170.8 centimeters tall. That's just over 5'7", okay? Assuming the normal model is appropriate, and the standard deviation for men is about 8 centimeters, what percentage of Dutch men will be over 200 centimeters tall? So the first thing we want to do here is draw a picture, right? This is a normal model, so we're going to draw a picture. And my picture is going to look like this, right? That's my bar down below here. This model says that at this very center, the mean is 184. And then we're going to go over 3 standard deviations. Notice that I'm making the spaces between the standard deviations fairly even, right? And each of these standard deviations is 8 centimeters. So if my mean is at 184, 1 standard deviation over is going to be 8 centimeters above that, or 192. And then this is going to be 200, and then this is going to be 208. I also need to go in the opposite direction, and then I'm going to be subtracting 8. So this is 176. This is 168, and this is 160. Okay? So the question is, what percentage of Dutchmen will be over 200 centimeters tall? Well, let's take my highlighter here, highlight 10. We're going to highlight the section that is over 200 centimeters tall. So here's 200. All of these people over here are over 200 centimeters tall. So what percent is that, right? And by the way, this goes on forever. This goes on forever and ever that direction. Well, we know that between the between the 2 standard deviations, that's where this is, 1, 2, that's 95%. Okay? So this middle area is 95%. If that's the case, what percent is on the outside here? If this middle is 95%, it means that this outside has to be 5%, or over here, 2.5, and over here, 2.5. So what percentage will be over 200 centimeters tall? 2.5%. Because the middle between the 2 standard deviations is 95. which means the outside has to add to 5. So we cut that in half, 2.5. Right? Let's take a look at another one here. So the next one says, what percentage of Dutchmen will be over 168 meters tall? Okay, well, again, let's highlight the area that we're talking about. Over 68 centimeters tall. So here's 168, which means we're talking about all of this space. Okay, all of this space. So what's my percent? Well, I know that from here to here is 95 because it's within 2 centimeters. And I know from the last question that over here is 2.5. So what percent is over 168? 97.5. Because this middle section represents 95% of the data, this section is 2.5, therefore they add together to be 97.5. What about the next one? What percentage of Dutchmen will be between 168 and 170? I'm pretty sure that that's supposed to say 176 because otherwise we'd need to do something else. This should say 176. So what's between 168 and 176? Well, let's turn on my highlighter. We are going for just this section right here. Okay, so that's going to be, you know, we got a little bit different here. We're going to have to do some extra calculating and use some logic. I know that between here and here is 95%. I know that between here and here is 68%. So if I were to take 95 minus 68, that would block that section out, leaving just these two sides. Well, since I just want 1, whatever's left of that, I need to divide by 2. Okay, you see the logic there? If the big section is 95% and the small section is 68, I can subtract them, and that'll give me the area of this section and this section. Dividing by 2 then tells me what just 1 would be. So 95 minus 68, that's 27, I think, right? Just doing some math in my head, 27 over 2. So that's going to be, what, 13.5 is what that section's going to be? 13.5%. So 13.5% of Dutchmen are between 168 and 176 centimeters tall. We got some more. Let's keep going. We got 3 more. I'm going to redraw my model up here. Okay. So that's a center of 184, and then 3 standard deviations over puts me at 192, 200, 208, and then this direction puts me at 176, 168, 160. Okay, what percentage of Dutchmen will be between 208 and 184? 208 and 184. So which section am I talking about? Here's 184. There's 208. All right. So what section is that? Well, it's not this bit over here. Remember that from here to here is 99.7, which means this section and this section is 0.3 for both of those, but that's 0.15 here and 0.15 here. Therefore, this section in the middle is going to be 50%, right, because it's half the data, minus 0.15%. So it should be 49.85%. So notice, again, what I'm doing. I'm highlighting out the section that I need, and then I'm looking at that 68, 95, 99.7 rule to figure out exactly how much I'm going to need here. Okay, what's between 176 and 192? All right, 176 is here, 192 is here. Look, that one's nice and easy because it's between 1 standard deviation. That's 68%. And finally, what is over 208? Well, over 208 is just this section right over here, which we determined. We had to figure that section out so we could do part D. That's 0.15. 0.15%. Which tells me that if I have a z-score above 3, only 0.15% of the population is that high, right? Is that tall, which is a very rare event. All right. So that's gonna call it for this video. This is a introduction to how these numbers within a normal model work. It was if we have something exact on the standard deviations. In the next video, we're going to talk about exact percentiles. What if the amount here is 195, right? If it doesn't fall directly on a standard deviation. That's what we're going to learn in the next video. Thank you very much for watching, and we'll see you another time.